Hi guys, welcome to today's lecture. Today we continue with our discussions on bivariate analysis techniques, and we explore the third case in numerical bivariate analysis techniques where we have two quantitative variables, and in particular we will introduce simple linear regression. So far we have covered two tables of the first bivariate analysis techniques, graphical bivariate analysis techniques and numerical bivariate analysis techniques for two qualitative variables, as well as one qualitative and one quantitative variable. Next, we move on to the case of two quantitative variables and see which numerical techniques we have in order to study the association between two quantitative variables. In our course here, we limit ourselves to the case of linear association between two given quantitative variables. In order to analyze the linear association between two given quantitative variables, we use a statistic called covariance. Covariance, as its name suggests, measures the amount of covariation between two given variables x and y, and being calculated using this formula. If covariance is 0, there is no linear association between two given variables. If covariance is positive, there is direct linear association between two variables, meaning that the direction of variation of x and variation in y is the same. In other words, x increases, y increases. If x decreases, y decreases. In that case, we have a direct linear association between x and y. If covariance is negative, we have indirect linear association between two variables, meaning that if x increases, y decreases. If x decreases, y increases. In other words, the direction of variation, it's the opposite. The larger is the covariance in absolute value, the stronger is the linear association between two given quantitative variables. But we have no bound for the covariance, and that's a drawback for the covariance. In other words, we cannot say how large is large enough. Consider salary and expenses as two quantitative variables. I have already calculated their means. The mean of salary is 23.9, in other words 23,900. The mean of expenses is 20,100. The covariance between the two using the formula is 1/29 because I have 30 observations. The sum of each observation minus the mean in the salary times the difference of each observation minus the mean in the expenses variable. We do this for all observations. We sum this all and we divide by 29 and we get 35.3, which is bigger than 0. This is an indication that we have a positive linear relation between two variables. A better statistic which is bounded and used to measure the amount of linear association between two variables is the correlation. Correlation is the covariance divided by standard deviation of the first variable times the standard deviation of the second variable. Correlation takes values between 1 plus 1. The larger is the correlation in absolute value, the stronger is the linear relation or the linear association between two given variables. If correlation is 0, this is an indication of no linear association between two given variables. If the correlation is between 1 and 0, that means if correlation is positive, we have direct linear association. If correlation is between -1 and 0, we have indirect linear association. And remember that in practice, almost impossible to get 0 correlation, 1 correlation, or -1 correlation. For example, if I consider salary and expenses, once again, the standard deviation of salary is 6.8 and the standard deviation of expenses is 5.4. And I use the covariance value from the last example, 35.8 something, divided by 6.8 times 0.4, which is 0.96, which is very close to 1, indicating a very high, strong linear association between expenses and salary. Now, if the correlation between two given quantitative variables it's very high, this is an indication of a high linear association between the two variables. We can model the linear association between x and y using a linear function. Remember that we use a linear function to model the association between x and y only when the linear association between two variables it's high enough. The model which we use is called simple linear regression model, as the form of y is equal to a plus bx plus u Y is, in this case, is called dependent variable, X is independent variable, A is the intercept, B is the coefficient, and U is the residuals. Residuals is the difference between the observed values and the predicted values. Then we use estimation method called least squares in order to estimate A and B. Once we have A and B, we just put the values here. We write Y is equal to A plus BX, which is the simple linear regression model between X and Y. We have different terminologies for X and for Y. Let's go through and check. For given two quantitative variables, which one is dependent and which one is an independent variable should be specified by the theory. If we use a linear function to model the relation between X and Y, it's interesting for us to check how much of variation in Y being explained in variation in X. The more closer are the points to this line, which is the scatter line, the more variation in Y is being explained by variation in X. The far are the points from the line, the less variation in Y being explained by variation in X. Why the amount of variation in Y being explained by X is important? Because we want to know by change in X how much change in Y would be explained. In order to numerically specify the amount of variation in Y being explained by the variation in X, we use a statistics called coefficient of determination. Now let's see how we can calculate the statistics that we have just seen in the lecture note in R. I go ahead with specifying my working directory, calling my dataset, and see that two variables, expenses and salary. First, I start by sketching the scatter graph. I use the function scatter smooth $d first salary, then $d expenses. You can see that the line here is not completely straight line, but very close to a straight line. In order to measure how much the relation or the association between salary and expenses is linear, we use the covariance. As we said, covariance is COV, $salary, $expenses, and as you can see here is 35 is a positive number, indicating that there is a direct linear association between salary and expenses, meaning that as salary increases, expenses increases linearly, and that linear association is positive. In order to bounded measure, we use correlation $d salary, $d expenses, and which is almost 96%. 96% is a very high number, very close to 1, which shows a very high linear association between salary and expenses. Furthermore, I can test the significance of the correlation using the core.test $d salary, $d expenses, and you can see the p-value here. The p-value is almost 0. That means the correlation is significant. Now that we are satisfied with the values of correlation as well as the scatter graph showing a high degree of linear association between salary and expenses, I can go ahead with modeling this linear association using simple linear regression model. And R, I use L is equal to LM $d expenses tilde $d salary. Remember that first the variable which is on y-axis expenses, then tilde the variable which is on x-axis. Always this is dependent variable, this is independent variable. Now run the model. In order to see the outputs of the LM function, I use summary L and see a lot of information being produced. Interesting for the time being for us is the estimate of the intercept in its p-value, and importantly the estimate of the coefficient of the salary in its p-value. Actually, the model which is being predicted is as follows. You can write the expenses is equal to the intercept is 1.97 plus 0.75 salary, and this 0.75 is significant because the p-value is almost 0. What this indicates? This indicates that the expenses is equal to 1.97 times 0.75 salary. As salary increased by 1 unit, 1 Afghani, 1,000 Afghani or 10,000 Afghani, the expenses will increase correspondingly by 0.75 units. For example, if salary increases by 1,000 Fs, the expenses will increase by 750 Fs. That's how we interpret this linear regression model. To see the linear fit visually, I use a function called AB line L, which is this linear model L, and just use a different color for it. Color is equal to read, color read. So now you see here in the graph, this black line is the observed values, and the red line is the fitted values or the predicted values from the linear model. Now you see not a lot differences between the black line and the red line. As a matter of comparison, let me consider another example for which I use working hours and evaluation grade, and I want to see how much working hours and evaluation grade are linearly associated. In other words, we are interested to see if working hours of employees is important in their evaluation grade given by their boss. I start with scatter plot again. Scatter dot smooth $$ working hours, $$ evaluation grade. Okay, now you see completely different graph here. This is very far from being linear. This is an indication that the association between working hours and the evaluation grade is not linear. To make sure everything is consistent, we just go ahead with covariance and $$ working hours and $$ evaluation grade. And you see here it's 0.09. At 0.09, it's a very small number. Go ahead with a correlation, $$ working hours, $$ evaluation grade, and that's nothing but 12%. Because 12% is a very small number, and you can test the significance using the core.test function, $$ working hours, $$ evaluation grade. You can see that the p-value for the test is 0.51, which is bigger than 0.05 or 0.1 even, and therefore the correlation is not exact. We can go ahead with the linear model. I call it L1 is equal to M of $. First, the $$ and the variable on the y-axis, which is the evaluation grade, tell dot $$ the variable on the x-axis working hours, and then you can go for the summary of L1. And here again, if you check the estimated coefficients, is the intercept is 2.34, and the working hours coefficient is 0.1. But important here is that this coefficient is not exact. We can go ahead with and plot the fitted line. For that, I use AB line again. I use L1 as input, and I use a color, red color for this. And if you compare the fitted line, business red line, and the original line, somehow representing the observed values, there is a huge difference between the two. And this is an indication that using linear regression to model the association between working hours and evaluation grade is not a good choice.